Good morning, everybody. Thank you so much for the invitation to come here and talk. And I'm super excited and privileged to talk to you about some of the research that I've been doing regarding the intersection between environmental temperature, environmental heat, and ADME, absorption, distribution, metabolism, and elimination of drugs and toxicants. So to start out, we've known for a long time about the link between environmental temperature and drug action. So what I have here is a publication from the late 50s, before there was really any information on molecular mechanisms, on the enzymes that have anything to do with ADME. What they did have was, are the rats dead or alive? And so what they did was, in this study, they freezed and baked a couple of rats and threw sort of a panel of chemicals at them to see what the impact was of these temperatures on the toxicity of various chemicals. And what you can see is a number of chemicals here where heat decreased the LD50 of the compounds. This increases toxicity. And they didn't really know why. There was just this sort of a change in toxicity. There we go. So I want to talk about environmental temperature, and I feel kind of silly talking to a bunch of Arizonans about environmental heat. But the normal sort of thermoregulation involves heat from the environment coming into the body and the body expelling that heat out. However, when we have an increase in heat in the environment, a la standing outside in the middle of July in Tucson, the body is required to expel heat to match that which is coming in. We call this phenomenon heat stress. Now, what if the amount of heat, the body gets rid of decreases, or the amount of heat in the environment increases beyond a level that we can sort of process in the human body? We call this phenomenon and the subsequent increase in body temperature heat strain. And heat strain is sort of the crux of my project. Now let's talk about numbers. In the human body, average body temperature floats around 37 degrees Celsius, give or take about a degree. And then when we're talking about high environmental heat, probably the first thing you think about is heat stroke. Clinically, we draw the line around 40 degrees Celsius. Anything higher than that is heat stroke. Heat stroke's not great for you. It's a multi-organ dysfunction disease, and it's the deadliest environmental condition to date. Now, what about this little area in the middle? Well, this is heat strain. And while it's not quite as deadly as its sibling heat stroke, there is still a milieu of physiological changes happening around these temperatures. And we think that's pretty interesting. And I do want to make a quick aside. This is for humans. Rats are sort of the underpinning of my project. Their internal body temperature is about a half a degree higher than ours. So sort of keep that in mind as we go forward. I'd like to take this quick moment to introduce you to your new favorite vocabulary word. So take this home and use it as often as you can. Phenoconversion. So what makes a person inherently susceptible to toxicity? The first thing that we think of generally is genetics. This is something that makes a person inherently susceptible to toxicity. Genetics. However, with phenoconversion, this is a transient change in susceptibility to toxicity that anyone can experience regardless of their genetic background. This is entirely environmental, entirely changeable. And so these phenoconversions can impact a number of enzymes and activities in the body. What I'd like to take a moment to focus on are some of the more exciting, some of the more common ADME-related enzymes. And so specifically, I'm talking about transporters here, phase 1 metabolizing enzymes, and phase 2 metabolizing enzymes. So let me give you a quick rundown. Under normal circumstances, compounds are taken up into cells by transporters, where they are modified by phase 1 metabolizing enzymes, subsequently conjugated by phase 2 enzymes, where these conjugates are transported again out of the cell into the bile duct and eliminated. And those compounds that are not are sent back into circulation. And this is sort of the groundwork of ADME. And these enzymes here, these transporters and phase 1 and 2 enzymes are the ones that I in my lab are most interested in. And so we wanted to look and see, is there any merit in assuming that heat strain and the subsequent phenoconversion of heat strain has any alteration on these phase 1, 2, and transporter enzymes. And so what I did was a data mine from an NIH database where a group was looking at liver toxicity in heat strain. They didn't care a little bit about these enzymes, but they did publish a transcriptomic data set that I was able to dig through and find out some of these proteins of interest. And what I found was a whole bunch of phase 1, phase 2, and transporters seems to be altered in the liver of heat-stressed and heat-strained mice. So this was really promising for this sort of hypothesis that maybe the changes in toxicities that we see related to environmental temperature could have something to do with some of these ADME-related enzymes. Ooh, that's kind of fuzzy. I apologize for that. So what I did to start was to find some model for heat strain. So in the literature up to this point, there hasn't been a lot of consistency in heat-related models, the way that they heat, the temperature that they heat, and the outcomes. And so what I wanted to do was find something that was more replicable, something that was more consistent. And so what I did at first was take some 8-week-old Sprague-Dawley rats and increase their environmental temperature to 33 degrees Celsius and measure their internal body temperature, and that's exactly what I did. We saw this increase in body temperature, as to be expected when you heat up rats, but unfortunately, the temperatures that they reached in this pilot study were a little too hot, so we had to pull them from the study due to them getting too close to sort of a heat stroke temperature. And so what I did was try to model something perhaps more environmentally relevant, hot during the day, cooler during the night. And what we saw was something a lot better. So we saw this increase in temperature and a return to sort of normal during the nighttime period here. Unfortunately, this wasn't quite heat strain, right? This was an increase in body temperature, but not to the level we wanted. We were about a degree off. So what I did was increase the degree that they were exposed to environmentally. So we bumped up to about 34 degrees Celsius, and what we found was sort of the jackpot here. The temperatures went up above this sort of heat strain line here. Not quite to heat stroke, though, so they were okay. They went back down to normal during the nighttime, and this was consistent throughout the entire week that we heat strained our rats. And so we looked at a few other biomarkers as well of heat strain, body weight. As you can see, the heat strained rats decreased their body weight over the week that they were in the stress condition. Their water intake increased, which is classic for heat strain. And we saw this increase in HSP70, which is sort of considered the classically heat-induced heat shock protein. And so we sort of hit all the markers of heat strain. So we wanted to look and see, were the changes that we saw in the transcriptomic data set, could we repeat that in our hands, in our heat-strained rats? So the first thing we looked at was transporters. So we did a targeted proteomic screen where we looked at a number of transporters. The ones I'm showing here were just sort of the ones that were changed. But we did see a change in transporters. And most interestingly, this change was almost exactly the same as the change in transport that we see due to the stress response after sepsis. And so what we saw was a heat-induced change in transporters and one that mirrored another similar stress response. And this was huge for sort of our hypothesis of, is heat stress changing these ADME enzymes? The next thing we wanted to look at was those phase 1, the cytochrome P450 family of enzymes. And these are particularly interesting because we can test not just the gene expression or the protein expression of P450s, we can assess their activity ex vivo. And so we do this with sort of an old school method. We take a specific substrate that is entirely reliant on a P450 isoform. In this case, I'm showing dextromethorphan and CYP2D1. Dextromethorphan is only metabolized by CYP2D1. And so any energy that is depleted when we incubate dextromethorphan and our liver sort of microsomes that contain P450s. We know it's exclusively due to CYP2D1. And so we use this sort of innate specificity of substrate and enzyme to measure the change in energy consumption in our hot rats and our control rat livers. And so what you can see is over time, the consumption of energy due to, in this case, dextromethorphan, so CYP2D1, is increased in our heat-stressed rats versus our control rats. And so what we see is an increase in the activity of this P450 enzyme in heat stress. So I replicated this with a number of other isoform-specific drugs. I've got that list here. And I chose these 8 particular cytochrome P450 isoforms because they make up around 90% of drug metabolism comes from these guys. So if you think of a drug, any drug, odds are they're metabolized by one of these cytochrome P450s. And so what we saw was really exciting, that 4 of the 8 top drug and xenobiotic metabolizing P450s seem to be changed in response to heat strain. Of particular interest, you'll notice here on the right, CYP3A1. That's the rat isoform of human CYP3A4 you may have heard of. CYP3A4 does about half of the metabolism of all of these P450s. So if you've got a drug, it's a flip of a coin whether or not CYP3A4 is somewhere involved in that metabolism. And this was, again, really promising for us because these enzymes may have some kind of role in the toxicity that we see because of heat strain. So just to kind of wrap up really quickly, 34 degrees Celsius exposure for 12 hours. This is our golden number. This is our magic number to induce heat strain consistently and repetitively in our rat model. P450 enzymes, of the top 8, 4 of them are changed. And then for transporters, we see this sort of uptake skewed decrease in transporter expression, again, like we see in other stress responses such as sepsis. So what does this mean for sort of ADME in general? We see a decrease in uptake transporters, and drugs that are reliant on uptake transporters will no longer be taken up into their cells, and they will remain in the bloodstream. This increase in retention could lead to potential toxicities. What about P450s here? Well, if we see a decrease in P450s, like we do with, say, CYP3A4, drugs that can come in will not be metabolized as they once were, and they will leave back into the bloodstream. Again, this sort of increase in half-life could also lead to potential toxicities. So what about like CYP2D6, where we see an increase in activity here? Drugs that come into the system will be metabolized rapidly. Some of them will be conjugated and will be able to escape into the bile duct and be eliminated. But some will not. Some will go back into the system. And this sort of release, this biotransformation, can lead to toxicity as well. And so I do want to just tie this kind of all back to the beginning. If you remember, DDT was one of those compounds that was changed at the beginning, a major decrease in LD50, so a major increase in toxicity. Well, it just so happens that DDT is metabolized by CYP3A1, and CYP3A1 is decreased in my heat strain model. So if we have decreased metabolism, what we see is an increase in DDT half-life in the body. And so increased DDT, a toxicant, would show an increase in toxicity, we would assume, in heat strain. So this could potentially be the mechanism, the model that validates a study that was done 70 years ago and hasn't been touched since then. So we are super excited to continue this sort of path of trying to discover the different mechanisms, the different stories of drugs and toxicants that could be changed in heat strain. So I do want to say a huge thank you to my lab, to the undergrads that have helped me do a lot of this work, specifically to Ben Rehnquist, who I don't think is here, but without him, I would have had a whole lot harder time kind of getting my heat stress off the ground, as well as my committee and the Environmental Toxicology of Human Disease, T32, that is funding me. Thank you very much.